So find me this page. Here we go. We're going to look at using formulas. Now, using formulas is an awful lot like stuff we've done already. This is going to be similar to checking those of you who have been doing this, checking your work throughout this equations unit. This is going to look very, very similar. You have this book. Where's your book? You got it at home. So I'll do 3 examples of the kinds of stuff that we're going to do. We'll talk it through and then call it a day. And then you guys can play with some of this stuff. The hardest thing for lots of people in this, and I get it, I didn't thoroughly enjoy this either. And for those of you who are dealing with English not being your first language, this is going to be even more irritating than it is for the native English speakers in the room. Is the fact that now everything is buried within, well, this and where we're going now over the next couple days, everything we've got is buried within English. We've got a paragraph here, for example. The speed of sound in water is 1,500, and then m/s means meters per second. The formula for the distance to an object is d equals 1,500 t divided by 2, where t is the distance in meters and t is the time in seconds. It takes 0.35 seconds for sound to reach a shipwreck and bounce back. How deep is the water above the wreck? So there's a lot that was said there. Effectively, what's happening is this. I'm going to draw the picture on the right-hand side of the page here. Is you've got a scenario where on the surface of the water, you've got a boat. There's our boat. On the bottom of the ocean, you've got a broken boat. It sunk. And we are given the speed of sound in water, and we are given a formula that uses that speed of sound to tell us that we are going to, well, it gives us the formula for the distance from this boat to this boat. Now, I get students all the time who are hung up on this. How does this relate to this? Why do I care that this is true? How do I know that what's going on here? Like, given the wording of the problem, this isn't necessarily obvious that this is what it's asking you to do. Why do we care what the speed of sound in water is, and why do we care what the formula for the distance sound travels in water? Why do we care about that? What is this ship doing that any of this is relevant? What do ships use sound for? Does anybody know? What does sound do when you shoot it at something or yell at something, sorry? Bounces back. So if you were like hiking in the mountains or whatever, and you yell and you say, hello, and then the mountain yells back to you, hello, you're not hallucinating. The sound has left you, it bounces off the mountain, comes back to you, we call that an echo. In a context like this, ships use sound the same way we would use an echo. Because we know how fast sound goes in water, we have a relationship for how far away an object is if we send out the sound and it bounces back. What is this? It's 5 letters, starts with S. This is sonar. So the problem with these word problems is that so many of them there are layers of expectation. We throw this together and like, oh yes, for those of you who are familiar with how ships work. You're like, oh yeah, okay, cool. So this thing, it's using sonar, bounces back. I'm going to figure out how long this takes. But the problem with word problems is that so many of us get hung up in the why do I care about this, that we get lost in what is all going on here. So that's what's happening in this case. We've got a ship on the surface, there's a ship on the bottom, and sonar is just a pulse of sound created by a ship, bounces off this, bounces back to the ship, lets you know there's something there. So, this first sentence, is there any information we actually need in that sentence? If you take a look at the rest of the problem, it says the speed of sound in water is this, the formula for the distance to an object is d equals blah. Did this first sentence add anything to our understanding of the problem? It kind of did, but if it wasn't there, if I just told you the formula for distance to an object is d equals 1500 t over 2, does that change anything? Not really. The only reason this 1500 is there is to plug it into this formula here, and it does. The question does it for us. So the hardest part with these word problems is trying to figure out what information here is necessary and what information here is unnecessary. That first sentence, given what comes next, is totally unnecessary. We don't need it. Because this value 1500 shows up in that formula there. So the second sentence gives us a formula. The formula for the distance to an object is d equals 1500 t over 2. If there's a formula in a question, pull it out, write it down. It's going to be useful. So we're going to pull out that formula, d equals 1500 t over 2. Don't necessarily know how we're going to use that yet, but it's a formula. Pull it out, write it down. It's going to be useful. The second part of that sentence actually gives us context for what these letters mean. What does the letter D mean? D is distance in meters, and T is time in seconds. So when they give you a formula, write it down. When they give you meanings for variables, record those too. Because now here in the second last sentence, this word problem says it takes 0.35 seconds for sound to reach a shipwreck and bounce back. How deep is the water above the shipwreck? Well, if this 0.35 is measured in seconds, 0.35, this number represents what? Time. So what am I going to do with that value right there? If this is a time, how is it going to show up in this formula here? Yeah, we're just going to take this value and we're going to substitute it right in there. We have 0.35, that's a time, it's measured in seconds. So it's going to go in there for t. If we plug that in there for t, we're going to solve this thing for d. D is a distance. Does that actually answer the question? The question is, how deep is the water above the wreck? Is measuring the depth of something finding a distance? Yeah. So this will, even though it's not worded exactly the same way, the meaning here is equivalent. So let's go, we want to know what the distance is. We're given a value for the time. Let's plug it in and solve it. So D is going to be 1500. When you replace a variable with a value, put brackets where the variable was, put your value inside it. And the rest of the formula should be written exactly as the rest of the formula was. And now we go ahead and solve this thing. You will be allowed to use a calculator for this stuff. So what's 1500 times 0.35 divided by 2? Anyone who has a calculator out right now, what is that? Josh, you're sleepy after lunch? Sleepy after lunch? What's that value? Anybody? Okay, so the number is 262.5. This is D equals this. D was distance measured in meters. So this 262.5 needs a context. 262.5 what? Meters. And now the last step is this. If I gave you the question in a paragraph, what do you need to do with your answer? What have you done in the past with word problems? Yeah. If I give you the question in a paragraph, you need to give me your answer in a sentence. So the question is, how deep is the water above the wreck? The water is 262.5 meters deep. And this is the skill set or technique we need to go through to do these kinds of problems. Questions about anything I've just done here? Okay, I'll model this twice more, 2 more problems, and then I will leave you with some work to do. Okay, here's the next one. It says let's practice, but I'm not going to say let's practice. We're going to do another example. In the following formula, big T is the air temperature in degrees Celsius at an altitude h meters. So there's a variable. There's a variable. We've got a T and an H. Big T is air temperature. H is the altitude at which this air temperature was taken. And lowercase t, these two T's are different, is the ground temperature in degrees Celsius. Here's the formula. So when you see a formula buried within a paragraph, pull the formula out. So let's write it down. Big T equals little t, and write it out exactly as it's written. In my C block class this morning, students were leaving off things. When you're copying it, copy it exact. That's a big T. That's a little t. Minus, this was getting just spontaneously dropped all over the place, h over 150. Now, we've been given some context here. Big T is the air temperature, h is an altitude, and little t is the temperature of the ground. Those are all measured in Celsius, because we live in Canada, not America. If the ground temperature is, so now we've got 3 variables here. So in order to do anything with this question, we need values for 2 of them. So the question says, if the ground temperature is 15 degrees Celsius, what is that telling us? What variable is this giving us a value for? It says the ground temperature is 15 degrees Celsius. Which of these 3 variables is ground temperature? The lowercase t. So this is little t equals 15 degrees Celsius. The question is, what is the temperature outside of an aircraft at the following altitudes? We're just going to do A. These are 2 different questions. This 6,000 meters is an altitude. Which of these letters represents the altitude as it was explained back in the question? H. So it says altitude of h, and then it gives us a value for the altitude. So this is going to be a value for h. This is going to be a value for little t. This is the formula that relates big T, little t, and h together. So being able to pull out these pieces is an important skill to be able to have. So what are we looking for? We're looking for the temperature outside an aircraft, the temperature presumably of the air. Because when a plane's flying 6,000 meters above the ground, we're looking presumably at the temperature of the air. So let's plug these values in. T equals 15 degrees Celsius. So I'm going to put that 15 where that little t is, minus, we're going to replace h with a set of brackets and put the 6,000 in there, over 150, and this is going to equal big T. When you organize your work like that, the steps follow naturally. And now I want to solve this thing. We're going to have to use bed mass over here. To big T is isolated. It's already alone. We just need to deal with this. What's the first thing we're going to do over here? Bed mass is brackets, exponents, division, multiplication, addition, subtraction. What do we do? The division. What's 6,000 over 50, or 150? So this is going to be 40. 6,000 over 150, so this is going to become 15 minus 40. This piece is this. And then 15 minus 40 is? Negative 25. So big T equals negative 25. Negative 25 of what? What is this a measure of? Big T was the air temperature in degrees Celsius. So this negative 25 should be degrees Celsius. And because the question was given to us in a paragraph, we have to give our answer in a sentence. The temperature outside the aircraft is negative 25 degrees Celsius. There you go. Let's do one more. Questions about anything you're seeing or experiencing so far? For those of you who have translators, you will be free to use them to give you context for the questions. I mean, obviously, that you practice your English is important, but at the end of the day, if the English is what's standing in the way of you doing the math, we'll translate it. Okay, last one. This one in questions like it always mess with students, because as soon as I start talking about specific animals, like this question is going to do, if you are not a kid, if you were not a kid who was interested in animals, like I was, for example, you might not know that this is even a thing. There is a creature out there called the giant squid. For those of you who are horrified of the ocean already, this isn't going to help. The giant squid is large. These things can be like almost a football field long. They're big. They're not super friendly. I would not want to end up, next to one of these. The reason they're so long is because they've got these crazy long tentacles. A football field is actually a little bit extreme, like half a football field, like 50 meters at the big end. It's still really big. So they have these things on their arms called suction pods. That's how they hold on to things. They grab stuff, and then using these suckers, they either can hold on to or let go of you. I'm willing to bet you probably have never experienced something like this. To give this a little bit of context, I have. I picked up an octopus on the beach. My buddies and I were trying to help it get back into the ocean, and it used its suckers to climb on my arms and then it bit me. So it was really quite cool. But I have personal context with what these suction pods look like, with what they do, with how they work. And on a giant squid, they use these to hold on to things they're trying to eat. So they've got these little hooks on those suction pods so that if you can get away from the squid, you're going to be scarred. Now, there's another animal in the ocean, those of you who might not know, called a sperm whale. And the sperm whale is about as big as the giant squid is, and they eat the giant squid. So you get these big whales, go down in the water. They are like, I want to eat you. And this thing's like, I don't want to be eaten. And so you got these massive animals that are fighting at depth. Now, the beauty of this whole thing is we didn't know about the giant squid for a really long time, but we did know about the whales. We know about the whales because they have to breathe air. They have to come up to the surface. We're on the surface. We get to see these things. So we would see the sperm whale. Whalers would hunt the sperm whale, and the sperm whales would come up out of the water covered in these massive scars. And so that's where these sailors were like, what the heck is down there that's giving these monstrous whales monstrous scars? And so like, there's this big squid down there. And then now we finally actually were able to see this thing. Giant squid exists by seeing the scars left on other things. Now this, I'm not sure how legitimate this formula is, but I saw the question. It was a good question. We're given a formula that relates the length of a giant squid with the size of these suction pods. Or this question says the formula that relates the length of a squid to the diameter of the suction pods. Now remember, diameter is the distance across a circle. Is this. L equals 180 times D. When you're given a formula, pull it out, write it down. We know the relationship between the length of a squid and the diameter of these suction cup pods is L equals 180 times D. Now this question says, what is the diameter of a suction pod on a squid that is 360 meters long? Squid do not get 360 meters long. That is terrifying. That's like the Kraken. Kraken doesn't exist. But how is this question different than these two? There is a difference between the first two questions and this third one. What do you see? Hasanjo? We don't have the diameter. Almost. Except for one, right? Like everyone leaves off something. This one was D equals whatever. This one was T equals whatever. We were given the time in this case. And in the second one here, we were given the ground temperature and the altitude. This time, we are told that the length is 360. So where is this value going to get substituted into this equation? It's going to go in for L. So the reason I tossed this example up here is in the first two questions, both of the formulas were already solved for the thing we were looking for. In the first one, we wanted distance, and we were told that D equals blah. In the second one, we wanted temperature outside the aircraft, and we were told temperature outside the aircraft equals blah. This one, we're told that the length equals 180 times D, and we're given the length. L equals 360. This thing is going to get substituted over here. So there are two ways that you can go about doing this. One way is if you can see that what we're looking for is the diameter and that thing isn't isolated yet, you can do what we did yesterday. We spent a whole bunch of time isolating for different letters yesterday. So if I want D, I can isolate for it. We can say, well, one way to do this is to rearrange to solve for the thing that we're looking for. Okay, I'm going to 180, divide by 180, divide by 180, and we're going to get L divided by 180 equals D. That's one way we can do this. We can start by isolating for the thing that we're looking for. Conversely, though, Abdal, wake up. Oh, you're writing? Okay. Conversely, what we could have done is, looking at this thing at the outset, we know that L equals 180D. I could just substitute this thing straight in here. We know the length is 360. I could say that 360 equals 180 times D. And then I could isolate for D. It doesn't matter which way you choose to take it. You're going to get the same result either way. Either way, if I do it this way, I substitute the 360 in for L, and I want to solve this thing for D, so I'm going to divide by 180, I'm going to divide by 180, and we're going to get D equals, I'll give you the value for this, 360 over 180 is the same thing as 36 over 18, which is 2. Or likewise, if I set it up like this, and then plug the 360 in, I'm still going to get 360 over 180 equals D. Either way, we're going to get that D equals 2. Presumably, if this is a 360 meter long squid, this is 2 what? If the squid's 360 meters long, the diameter of the suction pod is 2 what's? What should the units on this thing be? We're only given one other unit in the problem. It should be meters. And so for what that means is, for a squid, that is 3.5 times the length of our football field. A single suction pod would be a circle this big. Would be horrifying. This is a ship destroying creature is what this is. Just to give you context of the problem. Okay, so the last step here, we're given the question in a paragraph. We need to give our answer in a sentence. Oh, that's the wrong color. That's okay. The diameter of the suction pods is 2 meters, period. Done. So this is the kind of stuff I'm going to get you guys to do today. There's a bunch of different contexts to these kinds of problems, but this is what you're going to look at for me. All help where needed, but the easiest way for you guys to start to figure this out is to play with it. So I've circled most of the ones I want you to do here. I want you to do question number 1. I want you to do question number 4 over here. I want you to do question number 3 way down here. And I'm going to add question number 2 in there. Let me explain question number 2 before you guys get away from me. Question number 2 is similar to the first example that I did. It says, okay, gentlemen, Bilal and Abdal and Abdul, you are a sonar operator searching for a wreck that is known to be in the 900 meter to 1,000 meter of water depth. Your sonar, so the thing that you're using to create those sounds, has generated this table down here. This is a grid like Battleship. Hands up if you ever played Battleship. Not enough of you. In Battleship, for those of you who have never played it, you are trying to sink the other person's little fleet of ships, and you give your guesses for the location of those ships using these coordinates. So you'd say, like, is your ship at B2, which would be this square right here? Is it at D4, which would be this square down here? So this is a grid created by your sonar system. And these values inside the grid represent the amount of time in seconds that it took for the sound to travel to the bottom and back to your boat. So these values here are the time values you're going to use to solve this problem. You have 16 locations. Using the formula that we use in our example, d equals 1,500 times t divided by 2, you need to decide, based on this time information, where the rec is on this grid. The other questions are relatively straightforward. This is the only one that was giving my C block some grief this morning. So this is what I want you guys to take a look at. Question 1, 2, 3, and 4. 1 has parts A and B. 3 has parts A and B. 4 has parts A and B. And then I want you to flip the page. I want you to question 1. I want you to question 3. And I want you to do 12 and 13. So there's 8 questions I've given you and 35 minutes to do them. There should be time for you to make a reasonable dent here. You do not have a lot of space, so please do not cram your work into here. Either use your own paper. I have blank paper at the front that you can use and hole punch if you'd like, or the whiteboards are free and you can erase whatever's on them for you to tackle these 8 questions. This is your task. Let me know if you need a hand. On your mark, get set, go. Which question? The water. The one that you're working on. Yes, let us find. Yeah. Oh, which question did I give you? I think it was this one. Yes, this one. This guy. Over by the printer. So that means your answer should be here. Your solution is incorrect. You're close. You at 1,383,000. It's 1,450,000 something. Yeah.
Can I see the solution though? Like,
yeah. Would you like me to print it off? Yeah, I can print
it. Like,
yeah. Yeah, I'll print you the solution. You head over to the printer. Here you go. It's coming up. And it's double-sided, Sean. Yes, you may. Yes, you may. Put your guys, put your names on the board. Over by the printer. Don't let Austin Joe get demonstrate all of them. You all should be doing all of them. So there's two solutions on there. The front way and the back page. Okay.